I'm Bruce Bugbee, president of Apogee Instruments, and in this video I'd like to show you how we used Apogee Instruments to monitor the radiation characteristics that occurred during the solar eclipse, which happened a few days ago, and as everybody knows, went across the United States. Didn't quite go across Apogee Instruments headquarters here in Logan, Utah, so a couple of colleagues and I went to Rexburg, Idaho, where it was right close to the very middle of totality. So I'd like to show you how close the eclipse was to the Apogee headquarters. We went up to Rexburg, Idaho, right here on the map. Logan, Utah is right below Franklin County. It's about right here, and we just drove up to Rexburg, right near the center line. So we got an excellent viewing angle for the eclipse. We had a camera running the whole time to record how dark it got, and for people that were in 96–97% totality, that's not nearly the same as being in 100% of totality. This is a video we ran with, here's the Apogee setup here, and I'm going to talk about these in a minute. We had 3 laptops recording this. We all had our solar glasses. This is just a 30-second video to give you a sense of how dark it is. Here we go. This is a colleague, Tyler Volk from New York University, that's written like 7 books now on mega patterns, and he went with us. Right here is when it's close to totality. You can see it's not quite as dark as a full moon. That lasted 2 minutes and 20 seconds in Rexburg. We're not going to show you the entire 2 minutes. We sped it up here. Starting to get light. I'm getting pictures. The street lights came on. It's dark. And now the sun comes out just a crack, and it very quickly became light out. So this is in a rural area, not rural, sorry, it's in Rexburg, Idaho, but it was not near downtown. So we had a lot of neighbors coming by, all kinds of neighbors, and we took a picture with the neighborhood kids, which were especially interested in the whole thing, right after the sun started to come back out. Here's the instruments we used. We used an Apogee net radiometer here. We used an Apogee quantum sensor here. 3 spectral radiometers to look at color changes during the eclipse, and up and a down infrared sensors to do sky temperature and ground temperature, and then of course an Apogee aspirated shield for precision measurements of air temperature. These next several slides now show you the changes that occurred during the eclipse. This is not what we might call rocket science. NASA measures this stuff as well. It's just that here we were measuring it ourselves, not relying on NASA's data. This is the picture I took of the eclipse as it looked in Rexburg, and yeah, it looks like other people's pictures, just with the standard camera. Eclipses are really a unique event. They don't occur in other planets in our solar system. And let me see if I can show you how unique they are. There. Here's the sun. And in fact, I want to show you the sun in yellow to get it anatomically correct. There we go. Sun is 400 times bigger than the moon. Over here is the Earth, and we're going to put the Earth right there on this side of the screen. The moon, as everybody knows, is just a little dot right there. The sun is 400 times farther from the Earth than the moon is from the Earth, but the sun is also 400 times bigger than the moon, so the moon casts just enough shadow right there to give us a total solar eclipse. It's a remarkable thing, just happens in a small area. So what happened to the environmental conditions? The first one is photosynthetic radiation, and closely related to visible light. Here's the morning. Here's the sensor, an Apogee full spectrum quantum sensor. The morning here, we move the table just a tiny bit. There's a little hiccup. So this is going up, 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 up until the eclipse starts right there. And as soon as the moon started to move in front of the sun, it started to curve down. So we really had an hour, over an hour of watching the moon get closer and closer to the sun. It goes down, we get totality right here, and finally it starts to come back up. Everybody said, let's go, we're done, let's go. And I said, no, we got to wait to keep the instruments here till this levels out to complete the study. This point right here is when it's a solar total eclipse, is about as dark as a night with a full moon. And the interesting part of that is the full moon takes a long, gradual time. This happens just very quickly. Even 5 minutes before totality, it's still as bright as a cloudy day. It just is that moment right here. Full moon, put that up here, full moon, we usually consider to be 0.05 micromoles per meter squared per second. Now, we didn't have the adequate resolution to document this, but I know it didn't quite go down to this dark, and you could see that in the video. It was brighter than it would have been on a full moon, but still really dark, as indicated by going to 0. What happened to the other radiation characteristics? So here's the Apogee net radiometer. Here's the actual instrument right here. Remember that this has short wave on one side and long wave on the other. Here's the incoming and outgoing short wave. So the incoming short wave looks just like photosynthetic. The outgoing also decreased because there was less light to reflect. This was over a grassy surface, and grass reflects about 20 to 25% of the solar radiation. So let's look at the ratio of these two during the eclipse. Now the ratio of these two has a special name, albedo. This graph shows the albedo, and it's a flat line. And right here we get division by 0 because the numbers were so close to 0. It gets really noisy right in the middle of the eclipse. But the eclipse did very little to the albedo, the reflectance of the short wave. It shows how well the Apogee instrument worked because it's very flat through all of this. The other side of this does long wave radiation. You can see the black top. Here's the long wave. Look at these lines, very flat. The incoming long wave right through here is just remarkably flat. So overall, the sky temperature changed very little during the eclipse. The outgoing long wave dipped a little bit because the surface of the ground got colder without the radiation. So let's look at in detail at the surface temperature. Here's the net, which is all 4 components added together. It dips below 0 like it does at night, so the Earth is cooling because it's a negative net radiation. So the sum of these 4 numbers is the net, and it's negative. So that negative radiation meant much cooler surface temperatures and much cooler air temperatures. Let's start with air temperature. The line curves down here. The air temperature dropped from just about 20 to about 17. But look at what happened to the surface temperature. That went from about 23 down to about 12 during the eclipse. This is the temperature of the ground. Ground temperature is measured with the Apogee infrared sensor. We had one up and one down. I'll show you the up in a second. Notice that the air temperature and the ground temperature took a while to recover. After this radiation came back up, it took a while to warm back up. This was very noticeable. We were putting on coats in preparation for the cold temperature. Typically, the ground temperature is far more responsive to solar radiation than the air, as indicated here. This is the sky temperature as measured with an upward-facing infrared sensor, and look, very cold, minus 50 Celsius, and a flat line because the Apogee infrared sensor is designed to see through the atmosphere, close to seeing the infinity of space, so it gets very cold, and that temperature changed very little during the eclipse. We didn't expect that it would change, and it didn't. It stayed cold. Tiny bit of warming later in the day when the temperature came back up, but minimal effect on sky temperature. The biggest change was the colors of light. So this is our spectroradiometers measuring from 350 to 1,000 nanometers and measuring from during the eclipse to just after the eclipse. What we predicted was by blocking the direct shortwave radiation, the blue component of radiation would increase because of Rayleigh scattering. That's why the sky looks blue. The shorter wavelengths are reflected more and increase. It happens at different sun angles. So we blocked the direct radiation, and sure enough, during the eclipse, we got a higher fraction of blue light. Now keep in mind that during the eclipse, these lines were way down here. The radiometers picked up the blue shift, even though the intensity was many times less. It's because of auto-integration in the analyzers that we're able to do this. This is all normalized out here, so we can look at the relative spectral changes. So this was a great, fun study to quantify these changes. We measured all the data. Some of it was on the screen real time. People were coming by to watch it. And it is a fun documentation of the kinds of things Apogee radiometers can do during a solar eclipse. Thanks for watching. We'll look for you again in another video.